All right, folks, welcome back. In this lecture, we're going to focus on native code. And so let's get to it. All right, so you probably remember this slide from some past lecture, where basically we've seen how you can write Android apps. And in the past, we have focused on the part on the left, and while today we're going to focus on the part on the right. So the part on the left, we had this Java or Kotlin, generate Java bytecode, and then Davi bytecode, and then we already seen how you can actually try to go back, try to understand from the Davi bytecode, try to understand what's going on at the higher level. And in this quick lecture about native code, we're going to focus on, again, the part on the right. You can write some components of your Android app in C or C++, and this generates a shared object, okay? So we're gonna see how it works and what are the bad repercussions on the aspect of reverse engineering and malware analysis. All right. So first of all, why there is this native code component? Well, it turns out some code components need to be very fast, and this native code trick allows developers to write CPU-intensive components in C or C++. Okay. As you mentioned many times, when you write in Java or Kotlin, this generates Java bytecode, which then is translated to Davi bytecode, and this somehow a bytecode, right? Is not instructions that your processor directly executes. This bytecode is actually executed by another process, the Davi virtual VM or Davi virtual machine, or whatever it is placed. And this VM needs to take this bytecode, interpret it, and execute it, and convert it to actual machine code that the processor can execute. Instead, with C++, we generate code directly for the processor. Okay, so it turns out it's much faster, and that's why some people use it. So it's there so that you can do, for example, math stuff or rendering of some GPUs, rendering of some graphical user interface things with this native code component. And Google somehow discouraged its usage for other things, other simpler things that you may have in your app. And it discourages this because, it's much easier to introduce, for example, memory-related bugs and security issues in native code with respect to Java. And, it's much more difficult to debug things and so forth. So there are a number of reasons why Google discouraged this, but it turns out the bad guys don't care much. And as we'll see today, the bad guys actually have a number of incentives to use this native code. So C++ code is compiled to machine code, and we have mentioned in the past that if you take a Davi bytecode, disassembly is actually very easy. Okay, so from Davi bytecode to actually the Smalley version of the bytecode is actually very easy. Okay, there are tools that can do this in a reliable and consistent way. Instead, for machine code, is not that easy. Okay, and reliably disassembling machine code in the general case is an open problem. There are many tools that we will see that try to do this, and many tools actually succeed in vast majority of cases. But there are ways and tricks to somehow make this disassembling very complicated. And in general case, this problem in the general case is still considered not really solved problem. Okay, it's like an arm race and so forth. So the big advantage of the Davi bytecode kicks in because there is a Davi bytecode verifier. So if you try to have a malformed piece of Davi bytecode, you really cannot run it on a target device because the verifier, before running it, would check that some properties hold. For example, you cannot jump in the middle of instruction and things like this, while there is nothing like this for machine code. You have a stream of bytes, and then the processor just executes one instruction at a time. And if there is some instruction that says jumps here, even if this here is somehow in the middle of another instruction, it's just going to do it. Okay. So native code is difficult to assemble, and the compilation is even trickier. Again, there are tools. Some of these are open source. Some of these are you need to pay for it, and some of these are actually very expensive. And in general, it's very tricky. Again, there are several decompilers nowadays that somehow attempt to go from machine code to the actual C-like representation. But again, it's a bit tricky. So if you have a benign application, and so forth. Usually these decompilers do a decent job. If you have something very obfuscated and so forth, then you may be in trouble. Okay, so machine code makes easier for the bad guys to introduce code obfuscation techniques, and unfortunately for us, the good guys that try to take an app and try to understand what it does, unfortunately this existence of native code makes the analysis of the Java one not enough to understand what's really going on. And from the conceptual point of view, the tricky part is that you have the Java part and the native code part, but if there is native code and there is native code you don't understand what is doing, then even the analysis of Java part could be leading to misleading results. What do I mean with this? Well, both Java and Dalvik code are run in the same security sandbox. So there is one user for each application, and then you have the Dalvik part and the native code part. They run in the same somehow in process, maybe different, but belonging to the same user. Okay, and the trick is that the native code can actually try to interfere without the Dalvik code, and the memory of the Dalvik virtual machine is actually used. Okay, so one trick is that the native code could actually jump in Dalvik code part and somehow modify the structure of the Dalvik code in a way that it does what something different than what it's supposed to do. Okay, so for example, you have the Java code that the Dalvik bytecode that shows, oh, you do invocation of method A, but actually under the hood you are invoking method B. Why? Again, because it could be the native code actually modifies some internal data structure of the Dalvik virtual VM or the Android runtime to actually point this A method to actually the implementation of B method. Okay. So again, in general, there are no barriers between this Java and native code. If you have native code and you cannot trust it, then you should be really careful in terms of trusting what you see in the Java part. Okay. It's rare to find apps that have native code that somehow try to confuse the reader of the Java part, but conceptually it is possible. And really, if you see native code, then you should pay extra care in general, because many weird things could happen. And many of these guarantees that you had from the Dalvik part and the Dalvik bytecode verifier are not there anymore. Okay. Turns out there are some ways for the Dalvik bytecode and the native code part to somehow communicate in a reasonable way. So the tricks I mentioned before are really hacks. Like, you start the native code and then you try to access the memory and then you patch the memory in a way that the Dalvik code would actually do something different. But of course, there are ways designed by the Android folks so that your Dalvik component, your Java, let's say Java part or Kotlin part of the app, can talk to the native code component. This thing is called JNI, or Java Native Interface. It's actually something that comes from the Java world, so it's not specific to Android. And again, it's done in the past so that you have a Java component and then you can have some specific parts written in C++ or whatever compiles to a shared object, and you can communicate with them. It's important here, the communication is both ways. So you can have a piece of Java code that invokes a native method. Again, native method, what is it? Well, it's a method that is implemented in a native component. And you can have a native method, so a method in the native component that somehow is able to invoke a method defined in the Java layer. Okay? So how does it actually work? Okay, so here I have a small demo in the slide. So here you can see I'm cutting the content of this main activity of Java. So it's the main activity written in Java code, and that's how it looks like. Somewhere, of course, I have class main activity, define on create, blah blah blah. But somewhere I also have this public native string from JNI, and then I have this weird static and system load library. So what does it mean? Okay, the first line, what it's saying is, you know what? There is going to be a method called string from JNI, which does not take any argument and returns a string, and it's native, which means that you're not going to find the implementation in the Java component, but you're going to be able to find it in somewhere in one of these shared object libraries. Okay. Good. So this somehow declares the existence of this method. The second line, this static thing. So first of all, I don't remember if we've seen this in class already, but in a Java class, basically you can write this static, open curly bracket, some code, close curly bracket. This is a piece of code. It's also called the class initializer. This is a piece of code that is going to execute whenever you load the class for the first time. Whenever the VM loads the class for the first time, it's going to be executed. Okay, it's different than constructor because the constructor is if you do a new or if you instantiate a new object of a given class, the constructor kicks in. Here, even if you don't instantiate any object of the specific class, this one kicks in only once. Okay, again, class initializer, this is going to run whenever you load the class for the first time. And in bytecode, you're going to see this in a method called CL_init. Okay, like the init less init close with the CL, class initializer. Okay, so also vice versa. If you open the bytecode and you see some method called less CL_init and close, greater than, then that's a class initializer. All right, cool. In this class initializer, what we write here is system.load library natively. So what's going on here is that we are telling it that the first time we load this class, this main activity, here is going to try to find this native lib, which points to a shared object, and try to load it, so that the next time, the time we try to invoke this string from Genai, we're able to somehow resolve it. Okay, so the idea is that the string from Genai is implemented in a shared object with this name. Okay. So on the other side, we are now trying to focus, this is a shared object. That's how it's implemented. Here we have native lib.cpp, and that's how it looks like. Somehow we need to, we need to respect some conventions to somehow specify that the Java world expects a string from Genai method, and we need to, follow some conventions in the native code part to somehow make possible for the Java part to discover and resolve the symbol associated to string from Genai. One of the conventions is the following: check the method name that we implement in this C++. It should be something like this: Java _ .MOBISEC test. This is the package name, activity name, and the method name. Okay, so this huge method, it needs to be like this. And again, this, if you follow this convention, the Davi virtual machine or the ART system and so forth are going to be able to somehow link the string from Genai native method you've seen to this actual implementation of the native method. Okay, here then you need to take, again, these objects are part of the JNI, the Java native interface. So what I usually do is to take these templates and then use them in my code. And then you need to take this kind of environment object, and then this string from Genai, remember, it didn't take any argument, but it was not a static method. It was a method associated to an instance of the class, and that's why it takes the this, okay? And in this case, this J object thing. And here, basically, there's the code of the method. In this case, we are just instantiating a string, and then we are creating a string object and returning it to the Java world. Okay, so again, we define a string. This is a C++ string, and then we call this new string method. It's a method of this environment object, and somehow this creates a string in the Java world. A string compatible with the Java world. Again, the type here is called JString, and we're going to return it. And in the code, somewhere else in the main activity, once we do, we invoke string from Genai, we're going to get as output a string that actually contains hello from C++. Okay, and again, the cool part of this is that the piece of code in the main activity of Java or wherever it is can invoke the string from Genai method as any other method. So the caller of this method doesn't care whether this method is native or not. You just call it and you get back a string. Okay, and the magic of connecting this method call or this native method to the actual native code component in C++ or in machine code is done by the JNI machinery. Okay. Yeah. Cool. Again, as I mentioned, Java can invoke C++ methods, And since C++ methods can invoke Java methods as well. Okay, so it can be both ways. Okay, there's an example. So that's how we call from C++, we call a Java method. Before we have seen from Java to the C++. And here we have just a method. That's a normal Java method that once called just prints on a standard out something like this. And here we have the native method from before. And this slide somehow shows how from this getGeni string method, we're going to somehow invoke back the message_me method of the C++ component. Okay, so it's a bit complicated, but again, once you get how it works, you can just copy paste, maybe don't even take this template. Google for, example on how to call a Java method from native code in Android, something like this. You're going to find, even more updated templates. And, usually they have the package name and method name and class name you need to change, but after you change this, then it's downhill. And again, once you fix how to jump from one word to the other one, then the content is really up to you and it's potentially independent from Android. Okay, so let's try to dig in this. So in this case, what we're doing here is, first of all, we create a string of type JString. Again, this is a type that matches the string of the Java word. Then somehow we use this, again, remember, we take two arguments, the environment, some kind of context, and the actual object, the this. We use this environment to find the target class. So remember, the goal of this slide is to show how from the C++ code, we jump to the Java world, okay? And somehow the first thing we need to do is to find, to get a reference to the class type, okay, of the Java part. The way we do it is find class. So environment expose a method called find class, and somehow we can resolve where the main activity, a pointer to the main activity class type, okay? Then we somehow need to find the actual method. And again, it's very similar. Basically, we call the get method ID function. We pass the class, it was here, and then we pass the name and then the actual signature of the class, okay? The signature of the class, as we have seen in Dalvik, is literally the list of arguments and the return value, okay? And as you've seen before, the signature of this one was we take an argument that is a string and we return an argument that is a string, and that's why we have here ljava length string inside the parentheses and one ljava length string outside. Okay, one argument that is a string, and then the string is a return argument. Cool. Then we have basically we just do call object method. That's actually to invoke a method you just resolved, okay? And here you also need to pass the arguments. So this is actually the invocation, okay? And here is just to extract what we just returned. So basically, this method message me actually return a string, and here is actually how we extract from a JString. We actually extract a pointer to const jar, and that's how we print it, okay? Again, may look a bit more complicated. It's actually much easier once you have something working. It's much easier for you to actually take the example and then work from there. Okay, I think that's about it for this slide. Yep. All right. All right, so abstracting a bit more in terms of details. So at compilation time, we've seen already that once you compile your app, you get an APK. And in this APK, usually there is class.dex, manifest, and so forth. If you have a native code component, depending on how you set your Render Studio, you're going to have something like this, a lib folder. And then look at this, that's interesting. Usually you have x86 native lib so, or ARM v7a native lib.so. What is this stuff? Well, in the Java world, we compile to Dalvik bytecode, and the Dalvik bytecode is executed by the Dalvik virtual machine. And this Dalvik virtual machine, so the Dalvik bytecode doesn't care if you are going to be executed on a machine with the Intel CPU like x86 or with an ARM CPU. Okay, it doesn't matter. Why does it matter? Well, because Davi bytecode it is what it is, and it's Davi bytecode. It's it's independent from x86 or ARM, and then is the Dalvik virtual VM or ART and so forth that is actually implemented differently on your phone with respect to maybe an emulator. So on my emulator on my machine, it's an Intel machine. The ARM system, the ART system or the DVM is actually implemented in x86. Okay, and this x86 code can be executed by my processor and takes the input, the Davi bytecode, and executes it. On your phone or my phone, it's an ARM-based device. So on my ARM-based device, this DVM or ART components are actually in ARM. ARM can, of course, execute code written for ARM, so machine code for ARM, and this ARM thing is going to get the same bytecode as input and somehow execute it. Okay? For machine code, of course, it's different now. If we take our C++ code and we compile it, well, if I compile it to x86, I cannot run it on my phone. You cannot do this. Okay, so that's why when you compile a native code component in your Android app, usually you're going to get multiple versions of the same shared object. So in this case, this example shows that you have two different implementations. One is for x86 and one is for ARM. Okay, so unless I do this, unless the compiler actually creates two different versions, I couldn't run this on both devices. Okay, so for example, if the compiler only generates something with libx86 and libso, but not the ARM one, I could run properly with on my emulator, but I cannot run this on my device. Okay, so long story short, usually Android Studio or the compiler toolchain produces different versions of the native code, and so that it's possible to run it on your emulator or on device ARM or on the other device with different processors. Okay, that's somewhere in the settings. Okay, at installation time, basically the system somehow tries to figure out, hey, okay, classic.exe is bytecode, I know how to run it, and then, oh, there is a piece of native code. So, and then the system knows, okay, I'm an x86 based machine. Is there a library, like a native code library implemented for x86? If yes, great, I'm gonna load it. If no, bam, I crash. Okay, and I'm gonna say, I cannot run this on this machine. Okay. So that's let's say the resolution. Where are they going to be placed? Well, there is it also depends on Android. I think the latest version is something like this. So once your APK is unpacked, there is a lib folder where these things are put inside. But again, you need to have the correct version for your emulator, for your phone. Otherwise, it's not going to fly. I hope it's clear why once you compile it or once you take existing APKs and you unpack it, you may find different versions for different processors. I hope at this point it's clear. Okay, another interesting thing about native code is that you can actually create a native activity. And so you could have an app with no Java code at all, okay? Yeah, so the other thing is the shared object doesn't need to be embedded in the app. So you could load a native code from different parts of the system, and a common malware pattern is that you download something from the web and then you load it, okay? But of course, there are different tricks. So if you put it in the correct folder, then it's gonna automatically work if you do the load library thing. If you download the file somewhere else, then you may have different syntax to actually make it work. There is a link here. I'm a bit I think this stuff was working up to the Android 9. I'm not entirely sure this actually works on Android 10 or Android 11. I remember that they introduced some more security mechanisms so that you cannot just load a piece of code if it's not like in the specific folder. But I need to be honest, I don't remember the extent to which this protection refers to other piece of random bytecode that you download from the internet or every shared object in general, and so forth. Okay. Of course, there are ways to bypass it. Like you could have your own your own piece of native code, the one imported in your own app that somehow disables this the security mechanisms and so forth. But it could be that if you try to play with the example of just downloading a piece of native code and just run it, it may not work. Okay. So another question is JNI the only way Java and C++, C and C++ can talk? Of course not. And in general, I hope this is clear, right? They run in different, in the same, by the same user. And so there can be many tricks in terms of sharing information. If you use JNI and then you have a malware analyzer that somehow understand this and somehow tracks kind of message transfer between this JNI very well-known channel, then you know what's going on. But of course, you can think about many different ways through which Java and the JNI, the native code component, could communicate. Random example, well, the Java component could write something in the file, and then the native code component could read something from a file. Okay, and then to reply, you could write something to the same file, and then the Java component could read some new content in the file. Okay, so again, fantasy is the limit. There are many different tricks, and you could have malware that tries to be super stealthy and somehow it doesn't want to get caught. And so it doesn't use the traditional JNI methods to just do some kind of message passing, but it uses other tricks. Okay. All right, in terms of setting up Android Studio, you go to the SDK manager. That's one we have seen at the very beginning. And then you need to click on this NDK, CMake, LDB, and then install them. And then you can create a new project with C++ support. And basically this is gonna create somehow a simple app with already some template with the Java piece of code and the native piece of code. And at this point for you is much easier to start hacking. There is a link to some kind of a guide. Again, we are not going to be asked to develop native code components for this class. The reason is that there are many resources online and also classes at Eurocom like MOBISEC that deal with binary things. So this class basically have this set of slides on these binary components. There is going to be one challenge on somehow, that somehow touches on this native aspect, but that's intentionally light in terms of material on this native component. There is a crazy amount of material on the internet, and if you have questions on this, please send me an email and I can point you to interesting things. All right, so previous set of slides, we have checked how we reverse engineering David bytecode, and now we check how to reverse engineer native code. Again, if you have listened to me, it should be clear that reversing native code, you should expect to be more difficult than reversing David bytecode. Okay. So, super quick intro. Well, if you need to reverse it, you have in your hands a shared object. Okay. You take an APK, and then somewhere you find in this lib folder .so file. SO file is an L file. Okay, it's like a Linux executable, or it's wrapped in the same format as any Linux executable. And again, L files can be full-fledged programs. So they are marked as full-fledged programs. They have a main. You start them on Linux. You know where to jump. Or you can have libraries implementing functions that can be called by other programs, and that's the shared object case. Okay. So again, a shared object is just a piece of code that defines some symbols and some codes, and somehow they can be loaded and used by other programs. And if I need to use string from JNI method, I know where to jump. Okay, and I know how, that defines the implementation of the string from JNI method. Okay. Of course, you have seen this already in shared object. If you have a normal program that calls printf in C on Linux, well, this probably is linked against libc.so. Okay, so you probably used already shared objects and maybe you didn't even realize it. Same things in Android. In terms of tools, there are some tools to extract some metadata about these shared objects, and then to disassemble them, and then to decompile them. And I have a brief list of potential tools that you would use. There are also full-fledged programs to explore the binary. So through a nice UI, you can say, okay, show me the list of functions. Then you can click on it. You are going to see the code, and then, oh, please show me the graph. Bam, you have a graph. or okay, now show me the hexadecimal representation of this code, and then bam. Okay, so these are more in the commercial products, but not only commercial programs. There are also open source programs that somehow try to integrate the different tricks of the different aspects of seeing metadata, disassembler, the compiler, and maybe making these three things available at some clicks, at the reach of some clicks. Okay. So in terms of tools, one of the most popular, to start with is readelf. It's probably installed already in your Linux machine, and somehow it dumps all the metadata in the elf. Okay, you can run this on binary like binary. You can run it on a shared object. It's going to work the same way. OBJ dump is a program that I used a long time before getting more familiar with more advanced tools. But basically, what it does is it takes the program or the shared object, and somehow one of the things it can do is to disassemble it. So what it does is to take a program or take a shared object, tries to see the symbols, where the symbols point to. Symbols could be function names and so forth. And then it tries to do a disassembled scan. So it does a very simple algorithm, use a very simple algorithm. It's called linear sweep, or basically it starts from a specific point and then it goes forward. Okay. If you have benign code, this usually works. If you have malicious programs, that somehow, as long as all the instructions are one next to each other, this stuff works pretty well. If you have instruction that intentionally jumps in the middle of something else, of course, this is not going to fly. And so what we're going to see at a certain point is a bit garbage. Okay, but in terms of quick disassembly things, is actually pretty okay. Then there are of course other tools. Let's say the most popular in the industry is IDA. IDA Pro is very expensive. I think there is a limited free edition, but you can do that much. And you can disassemble things, you can show graphs. I think there is not a compiler in the free version, and actually the compiler is so powerful that is actually sold as a different component. So once you buy IDA, doesn't mean you have the compiler. You need to also buy the plugin for that implements the compiler. Okay. There are many tools out there, many of which are open source. Radar 2 is one of the most famous disassembler, or some kind of toolkit or framework for binary analysis, and it's actually very cool. I started to use it only very recently, but I'm very happy with it. Basically, it's Radar is mostly about command line thing. So you open the binary in the command line, and then you can do things like go to a specific place, start dumping some bytes, or start dumping some instructions, and things like this. Then the Radar people built a cutter. It's like a UI for Radar 2. Again, it's also open source. And the cool part is that they integrate also other free tools, such as, for example, Ghidra, written below. So Ghidra is an open source tool written by NSA that's been released, that's been in the building, in the making for, I think, 10 years plus, but has been open source, I think, last year or 2 years ago. And it also has a quite cool decompiler. And so, for example, the Cutter guys somehow integrate the Ghidra decompiler in the Cutter UI. And so, if you don't like some Ghidra feature, but you like some other feature, then you can have the Ghidra view inside Cutter. Again, it's very actively maintained. These guys are very nice. So usually they are proactive in fixing things and so forth. And they're very receptive of pull requests and fixes. Okay. So again, these are the free ones. Reddeck is also open source. It's a compiler from Avast. I never played much with it, but I've heard good things. Then again, in the more not open source or not free tools, there is Jeb. It's not open source, but there is a free version available. Jeb, I think, could be considered the best in terms of Android app analysis. Again, I didn't use it that recently, but I used it in the past, and it was really making the analysis great. He also has a bunch of disassembler and things like this. But again, in terms of Android part, is actually pretty good. You can disassemble Android apps, as we've seen last time, with other tools like Ghidra and so forth. But the support these tools have for these specific Android things is a bit less nice, let's say. There is also Binary Ninja. It's not open source, but it's affordable. And it's actually super nice UI, and very cool guys behind it and so forth. In terms of the industry, I think we could say that the status quo is more to use IDA, and it is very powerful. Okay, that was the end of the quick intro. There are going to be some more details in the demo. Again, this was a very short intro on the topic just to get you started. Again, there is only one challenge where you need to have some brief understanding of what's going on in terms of native code. Again, if you can take the binary and disassemble it with one of these free tools, then you are good to go for this class. Again, I just wanted to touch on this topic because I think it's important you guys are aware of it, that it's a big area, but I didn't want to spend too much time on this because there are so many resources out there publicly available that it would have been a bit of a loss of time. Okay, and with that being said, that's about it, and yeah, happy hacking.